Hi, let's talk today about a couple more concepts, which are the first moment of areas and lines, as well as symmetric areas, before we actually see how we can determine the centroid of composite plates and wires. So let's start with the first moment of the area. And what is a moment? If you remember, the moment of a force is the tendency of the force to rotate about a point, and it's calculated by multiplying the magnitude of the force by the moment arm, which is the distance from the force to the point about which we calculate that moment. Now, we can calculate the moment of an area just by multiplying the area times the moment arm, which is the distance from the centroid of the area to some point about which we calculate this moment of the area. Therefore, by definition, we can denote qx as integral over the area of y dA being the first moment of area A about the x-axis, and similarly qy, integral of A over A of x dA, would be the first moment of area about the y-axis. Now we also know that y bar A times y bar A equals to integral over the A of y dA, and also x bar A equals to integral over the area of x dA, and therefore we can express the first moments of area as qx equals to y bar times A and qy equals to x bar times A. You can see areas multiplied by a distance from the centroid to a certain point or axis. Now, if you look carefully and you think a little about these equations, you'll easily realize that if the first moment of an area calculated about a coordinate axis is 0, then the centroid of that area is located on that axis. And that's because areas with positive and negative signs on the left or right on that axis will cancel out, as you can easily imagine. Finally, if we express the first moment of the areas for lines, we will get similar equations. Qx equals to y bar times L and qy equals to x bar times L. So all we have to do is replace the area with the length of the line. Now, having said that about the first moment of the area, let's talk a little about symmetric areas. And we will see that there are two types of symmetry for areas and lines as well. And these are useful to determine the location of the centroid by inspection only. So in other words, if you can determine that a figure is symmetric, then you don't have to calculate or perform any calculations to determine the location of its centroid. Very easy, by inspection. There are two types of symmetry that we need to identify. And the first type of symmetry is the symmetry about a line or about an axis. And let's see what this is all about. I'm going to start by drawing a figure. This is an L-shaped figure, like so. And I'm also going to indicate an axis. Let's call this axis BB prime. And you can see, before we talk about the actual theoretical concept of symmetry, that if we fold this figure along BB prime, the two halves, the two portions of the figure will perfectly overlap. They will perfectly overlap. So that means this figure is symmetric about this line, this axis, BB prime. In other words, we can say that for every element P that has a very small, infinitesimally small area dA, there exists another element, let's call this one P prime, of similar area dA, which is located at equal perpendicular distances from the line of symmetry. So these two elements are located at the same distance from the line of symmetry, in this case from axis BB. As I said, in that case the figure can be folded along the axis of symmetry and it will overlap, the two parts will overlap perfectly. Now if you were to calculate for this case the first moment of area calculated with respect to the BB prime axis, this will be 0 because of the positive and negative signs of the distances to the elements P and P prime. So therefore, the conclusion is that the centroid of an area will be located along the line of symmetry, if of course that area has a line of symmetry. So we know that in this case, the centroid is located somewhere along BB prime. Now, if a figure has two lines of symmetry, then obviously the centroid of the figure will be located at the intersection of those two lines. So nothing to calculate. If it's only one line of symmetry, then you'd have to calculate the location of the centroid along that line in the other direction. The second type of symmetry is symmetry about a point. And again, I will demonstrate that by drawing a figure. And this figure resembles somehow letter S, as you can see. All right, and I am going to select a system of axes, which could be actually the coordinate axes, X and Y. And then again, a small element P, let's say located here, and another element P prime located at the bottom left here. Each of these elements are located at X and Y and negative X and negative Y respectively coordinates with regard to the system of axes. Now, if for every element P having an area dA that is located at coordinates X and Y, there is an element P prime of a similar area dA and located at coordinates negative X and negative Y, then if this condition is satisfied, O is a point of symmetry. And now if you look at the signs of the coordinates X and negative X and Y and negative Y, one can easily determine that the first moment of areas about the X and Y axes are 0. So therefore the centroid of an area that has a point of symmetry is located at the point of symmetry. So if you can determine that an area has a point of symmetry, that's also the location of its centroid. Very easily and straightforward, and no need to do any calculations. All you have to do in problems is to indicate that. Indicate the symmetry. Now, An area that has a point of symmetry does not always have an axis of symmetry. And this is exactly the example that I've just drawn. You cannot fold these figures along the x or y axis or any other axis for that matter in order to have it overlap perfectly. It's impossible. So this figure has only a point of symmetry and no axes of symmetry. Now, if we have a figure that has two axes of symmetry, that does not always have a center of symmetry, a point of symmetry. And it might sound a little strange, but let's look at another example. Say an equilateral triangle, like this one. And of course, this vertical line, let's call this one BB prime, is an axis of symmetry. And here's another line, DD prime, which is also an axis of symmetry. And now if we check the above condition, so this would be element P, and we select another element P prime equally spaced on the other side of C, the center of the intersection of the lines of symmetry. Well, element P prime falls off the area. It's not part of the area, so therefore C, the intersection of these two axes of symmetry, is not also a center of symmetry. However, in such cases where the two axes of symmetry for a figure are perpendicular to each other, then their intersection would also become a center of symmetry. Only in that case, the intersection of two perpendicular axes of symmetry will also represent a center of symmetry. So having said that and looking at these two basic principles, the first moment of the area and symmetry cases of areas, then we can now, in the next lecture, look at composite centroid for composite plates and wires. Thank you very much for watching this lecture, and I will see you at the next one.